Welcome to the exercises for chapter 14, all about integration. This first exercise is about using SymPy to integrate power functions, so functions of a variable with something in the exponent. So what you want to do is create this base function in a for loop in using SymPy, so symbolic expressions. So we have f of zeta, this is beautiful Greek character zeta, to the equals zeta to the power of kappa divided by 2. And then in a for loop, you change kappa from 1 through 6. So the first iteration in this for loop, we would have the function zeta to the power of 1/2. And then in the next iteration of the for loop, we have zeta to the power of 2 over 2, which is just zeta, and then 3 over 2 and 4 over 2 and so on. And then you want to calculate the antiderivative using SymPy, and then basically visualize that by creating this figure 14.20, and also figure 14.21. So here I'm just printing out all of the power functions. So here we have zeta to the power of 1/2 to the power of 1, 3/2, and so on up to 3, which is the same thing as 6 divided by 2. And then here on the right column, I show the antiderivatives of each of these expressions. And then here you can see I'm plotting in the single lines are the functions, and the dashed lines are their antiderivatives. And different color gradients for the different power values. So that's all you want to do, basically just to give you some more experience working with SymPy and integration and converting to NumPy to visualize in Matplotlib. Last thing I will mention before switching to Python is to make sure that the exponents are symbolic numbers. So you want zeta to the power of 3 divided by 2 and not zeta to the power of 1.5. Now, in some cases, this distinction matters. In some cases, it doesn't matter. Very often, it doesn't matter. But I want you to make sure that the expressions are symbolic numbers in this case, just to make sure that you really understand how to work with numbers and symbolic representations of numbers in SymPy. Here you can see I'm creating a symbolic variable. Now, when I write in sim.symbols and I put in the characters zeta, I'm actually setting that equal to a Python variable called g or xi, right? But so because SymPy internally recognizes these 4 letters as corresponding to or mapping onto the Greek lowercase letter zeta, this is actually going to print out in symbolic expressions as the letter zeta and not xi. Okay, so something I've mentioned several times before. Here is the numerical grid for plotting. This has nothing to do with the integration. We're not actually calculating definite integrals or evaluating numerically integrals here. This is only for the visualization. Okay, so here I have the for loop here. And here is the key to getting the symbolic expression of numbers. So I'm using the function sim.simplify with one of the numbers. And this is going to be the difference between 1 divided by 2 versus 0.5. Okay, so just to illustrate to you, if I did this, then here we would have, at the first iteration, here we would have x to the power of 0.5, because this term Python will evaluate to be 0.5, and then that becomes the symbolic expression. But here, Python is not going to interpret this as being 0.5. Instead, SymPy is going to take over and say, this is the symbolic number of 1. This is a symbol representing the number 1. And therefore, this whole expression here becomes 1/2. And now in SymPy, as long as you have one of the numbers as a symbolic number, then this one is also, the entire expression is going to be treated as symbolic. So it is not necessary to also simplify the 2 here. Okay, I think the rest of this code is fairly straightforward. Here I'm integrating this function according to this variable. So we are integrating with respect to Python variable xi, but that actually corresponds to symbolic variable zeta. Okay, then here I am printing out the function and its integral. And here I am evaluating the function and its integral into a list using list comprehension. Now, if you wanted to solve this exercise by lambdafying this function and then evaluating that lambda function, that's also great. That's fine. I chose to use list comprehension here for two reasons. One is that we don't actually need these numbers as a NumPy array. Sometimes we do. Depends on what we're doing with the numbers, with the function later on. But in this case, we're only plotting, and the plotting works fine for a regular Python list, as long as the list contains numbers. So we don't actually need this to be a NumPy array. That's one reason. And the second reason why I chose to use list comprehension is because this is the only place in this entire code where I actually need to evaluate this symbolic expression for specific floating point numbers. If we needed to get out, YF or these numerical values more often, then it would make sense to lambdafy the function. But here it's just once per for loop, just for plotting. So I think a list comprehension is just fine. Okay, so here we have all of the expressions printed out in LaTeX, and here we have the visualization. I think this looks pretty decent, not the most beautiful plot we've generated in this book, but it looks nice and smooth. I wrote in the book text, if you like, you can also modify this code to include visualizing the derivative of this function. In my humble opinion, the derivatives of these functions don't look as interesting, so I chose not to include them here. Feel free to disagree with me. Now for exercise 2 of chapter 14. The idea of this exercise is to write code to complete figure 14.3. Now I don't need to scroll all the way up to figure 3 in this chapter because the first two panels of this figure here are exactly figure 14.3. So what you need to do is basically write additional code to finish this figure. And if you'd like a little bit of an extra challenge, you can rewrite all of the code from scratch. So instead of copying and pasting the figure from my code to generate figure 3, you can just write this from scratch. Okay, so what do we see here? Here we see three functions in panel A. You can see, let me zoom in here. Here you can see these are all identical functions except for an added constant. So this has x squared over 10 plus sine of x plus 0 plus 1 and plus 2. Otherwise, the x terms are the same. So these three functions all share the same x terms, and they differ only by a shift on the y-axis. So that is this constant that's added here. And here, what I showed in the book chapter is that when you integrate these functions, when you differentiate these functions, their derivatives are identical. Of course, they are identical because the derivative of any constant is 0. So all of these differentiate to 0. So the derivatives of these functions are exactly the same. Now that is what I illustrated earlier in the book text. What you want to do here is integrate these 6 functions and visualize them. So we have 3 functions over here and 3 functions of the derivatives. Now they're all the same, but in code they will look different. Okay, and what is the point here? Well, I think I'll first switch to Python, show you the code, and then I will make some statements and interpretations about panels C and D and what they tell us about constants and the constants of integration. This cell here is exactly copy-pasted from the code corresponding to figure 3. Okay, so if you want to rewrite this out from scratch, that's great. You can see it's not so difficult. There's not so much code in here. Basically, we just define the function. And here I'm writing plus I, where I is this looping index over the different constants, 0, 1, or 2. Then we use SymPy to create its derivative, its integral, and then actually integrate the function. This is the integral of the derivative, and here is the integral of the function. Okay, again, this code cell here is exactly copied from earlier, from figure 3. This is the new code here. And this just involves visualization, so nothing too fancy going on here. Here I am evaluating the function and its derivative, so to get from a symbolic representation to a list of numbers. And here is the integral, so the integral of the function and the integral of the derivative of the function. And then I'm just plotting all four of these or I guess all six of these lines in these different subplots. Okay, so this takes a minute to run, mainly because this code here, this list comprehension and substitution method from SymPy is a little bit sluggish, as you have seen several times earlier in the book. Okay, so here we have panels A and B. Let's see, let's start with interpreting panel C. Now here what we see is that the antiderivatives, the indefinite integrals of these three functions, f, g, and h that we see here, are distinct from each other. They're not just shifted versions of each other. They really differ. They differ on the x terms. Now, why do they differ when these were all the same? Well, the thing to keep in mind is that these constants here in the function get integrated. So this turns into, well, this one turns into a 0 times x, so nothing happens here. Here, this is a plus 1. In the function g, the plus 1 is just shifting the entire function on the y-axis without changing its shape. But when we integrate this, the 1 becomes a 1 times x, right? So we add an x to this constant, and this becomes a 2x. So this is not just shifting the entire function up and down on the y-axis when we get to the integrals, but instead it's adding a scalar, this constant, times x, which is actually bending the function. It's tilting the function, not just shifting it up and down the y-axis. That's why it looks like these functions they look pretty visually similar to each other, but they are tilted on the y-axis. So the slope is increasing. That's because here with f, we have a added x term of 0, so no added x term. Here with g, we have an added x term of x, and here we have an added x term of 2x. And of course, all these functions touch at 0 because, well, the functions at 0 are still all 0. Okay, and then of course, these functions, the derivatives of these functions are the same, so of course the integrals are the same. What is the take-home message here? The take-home message here is to be careful. You have to be mindful about when and where you add these constants of integration. Because when you integrate a constant, you get a function of x with an x term in it. But when you integrate a function and then you add on a constant of integration after the integration is complete, then that added constant really is a constant. Okay, so this is a concept that will come up again with multivariable integration. So we're going to see this theme come back later in the book. Now for exercise 3 of chapter 14. The goal of this exercise is to explore using SymPy and then also SciPy to calculate a definite integral. And you will discover that SymPy is unable to calculate an exact analytic definite integral. And so therefore, we're going to use SciPy to estimate that successfully. Okay, so here's what you want to do. Implement this function here as a symbolic expression. So we have x cubed divided by e to the x minus 1. And then what you want to do is first actually just visualize that. You'll get a plot that looks like this. And then you want to try to calculate the definite integral of this function using SymPy from -1 to 3. So try calculating a definite integral analytically using SymPy. You will discover that it's not going to work. And we will see in a moment what the output looks like. Now, maybe you think this is because of the discontinuity that happens when x equals 0, right? So x equals 0, then this term equals 1, then we have 1 minus 1 in the denominator. But you can try this again. You can try calculating the definite integral using different bounds. For example, +1 to +3. So bounds that exclude this discontinuity, and you can see what happens. Okay. And then what you want to do is use methods that you learned about in SciPy for estimating the integral using accurate techniques. So you can use SPI.Simpson, you can use SPI.Quad. I don't tell you exactly how, or which method in SciPy you should use. That's up to you. I will show you my solution in a moment, but you should get a value of 3.027. So here we begin by implementing this math function as an expression, a symbolic expression. You can see I'm using a symbolic variable x here. Okay, and then I'm extracting x and y values to make the figure. And the figure looks exactly like how it looks in the book. Okay, no problem. We do get a warning message here. Now you know all about these kinds of warning messages. And of course, that happens when x equals exactly 0. Now, it's interesting also to consider the limit of this function as x goes to 0. If we try to plug in, we'll fail because we get 0 divided by 0. So this calculating the limit as we approach 0 is not specifically part of this exercise, but a little interesting side project you could work on. You should be able to get through that reasonably okay. All right, and then, well, you can also see from the graph that the limit as x goes to 0 of this function is also 0. Okay, so here we are attempting to integrate this analytically using SymPy. And you can see that, I use sim.integrate, so the syntax here is correct. But when we just look at the output is simply the input, right? So this is what we want. We want SymPy to solve this integration, but it doesn't actually solve the integration. It just gives us back the same input that we provided. And then, sometimes you can write eval f or do it to try to get a numerical solution. Here, I'm just showing you what it looks like when we use bounds that exclude the difficult value of x equals 0. Now, the issue here is just that this is a really difficult integration problem to solve. Okay, so therefore, we're going to use SciPy. As I mentioned a moment ago when I was showing the book chapter, there are multiple ways to use SciPy, multiple methods that you can use to estimate the definite integral with pretty good accuracy. In this case, I chose to lambdify the function and then use spi.quad. That is one method. There are other methods. You could use Simpson and so on. There's several ways you could do this. But yeah, here we see just the value printed out. This is inconsistent with what I showed in the book, and that's just because of the bounds here were -1. So I'll set that back to -1. And now we're going to get 3.0270. Now for exercise 4. The goal of this exercise is to write an algorithm in Python that will solve the initial value problem using SymPy. Remember that the initial value problem is basically where we are able to resolve the constant of integration because we are given an additional constraint. So a typical initial value problem looks something like this. Given a derivative, in this particular example, it's given f prime is 2x plus 3, and we know that f of 1 equals 2, solve for f of x, okay? So we're given the derivative, and we're given one value, and then we are asked to find a solution without a constant of integration. Okay, and so just as a brief reminder of what I discussed earlier in this chapter, the way to do this is to integrate this derivative to get the original function. That's going to give us a form of f of x plus c, right? Then we're going to have a constant of integration. And then we need to solve for this variable. So we plug in 1 for x, and we know the answer is going to be 2, and we have the unknown variable c, the constant of integration. And then we just do some algebra to solve for c, and that gives us the final solution, which for this particular problem setup looks like this. Okay, so there's 3 parts to this exercise. The first part is basically just to write code in SymPy that implements the initial value problem, that solves that problem. and then print out the results that look something like this. Then there's more to do with different functions. I will get back to that, but first I want to show you the code to solve the initial value problem. Writing code for this exercise is all based on things you've learned before. The only trick here is to explicitly define a constant of integration as a separate variable. So here I'm defining two symbolic variables, x, that's for our function variable, and then c, and that's going to be the constant. Here I define the derivative. So again, we don't know the function yet. We have to integrate to find the function. Here we have the derivative, and these are the initial values. Now there's multiple ways you could set it up. I chose to set this up in a list where the first number is x and the second number is f of x. So these are the constraints that are given to us by the problem. Okay, I will get back to this later. Okay, so here is step one. We integrate the derivative and we add a constant of integration. And there you go, it looks like that. Now for step two, we just use sim.solve, and we want to solve for, so we plug in, so in the function, which we got by integrating the derivative, we substitute wherever we see x, we substitute in the value of x, and then we have equals the value of the function at the value of x. And then we are solving for c. Okay, and then, yeah, the rest of this is just printing out the solution, exactly like how I showed in the text. The second part of this exercise is to basically run the same code. So you don't have to change the code. We're just working with a different function and a different initial value. So now we see that the derivative is x to the power of 5 over 2 plus cosine of x. And here is the constraints that allows us to solve the initial value problem. So we know that f of 1 equals pi. Okay, so then basically this is just a little thing in SymPy. I'll talk about this in a moment. But this is part two. And then part three of this exercise is basically to repeat again the same code, almost exactly the same function, but now you multiply these two terms instead of adding them together. And let's just see what happens. It gets quite complicated. Okay, so that I have up here. So here we have the derivative equals the symbolic cosine of x plus x to the power of 5 over 2. Okay, and yeah, then we can just run this again. Now, already here you can start seeing that this is a little bit strange, but I'm going to continue for now. Okay, so we get lots of really long numbers. This is fine. There's nothing really wrong with this, but remember in the text, I showed the fraction 5 divided by 2, and here this got converted into 2.5. Now, this is an issue with symbolic numbers and numerical floating point numbers that I have discussed in a previous exercise and also earlier in the book. Essentially, what we want to do is make sure that SymPy interprets this as 5 divided by 2, so as the symbolic fraction. Now, previously, I showed you one method of getting SymPy to treat numbers as symbolic objects and not as floating point numbers, and that's by using sim.simplify. And what I'm showing here is another method when you have a rational fraction. So basically just the ratio of two numbers. Okay, so now I'm using sim.rational, and we can already see how this changes, right? So now we get a symbolic expression instead of a floating point expression. Okay, so that will also change the output here. This looks much nicer. This is the form that you would get if you were solving the solution on a piece of paper. Okay, and then for the final part, I just want to, this is more for just exploring math in SymPy. So here everything is exactly the same. We're just multiplying these terms instead of adding them. Okay, and here we get, this takes a little while to integrate. It's a difficult problem to integrate. So this is a really long, complicated result of integrating this seemingly simple, straightforward expression. It's only two terms in this expression, and yet The integral is really, really complicated. And what is this funny looking thing? This is a gamma. This is an uppercase Greek letter gamma, and this stands for the gamma function. The gamma function is kind of similar to a factorial, so you're probably familiar with the factorial function where, for example, the factorial of the number 5 is 5 times 4 times 3 times 2 times 1. Okay, so the gamma function is a little bit similar to that, but it's quite a complicated expression. Okay, and then let's see if we can solve this one. Okay, so we do get a solution, and it's this really, really long sequence of terms. Quite complicated. If you are curious, then I definitely encourage you to explore this function. You can numerically evaluate this function for lots of different values of x and make a plot of it. That would be great. But I'm going to consider this a successful completion of this exercise. Oh yeah, I guess what I wanted to show you here is how even seemingly simple functions, when you integrate them, can become really complicated and really difficult to integrate. This is a huge difference between differentiation and integration. Differentiation is it generally much easier to do than integration, and this is one example of that. Here we are in exercise 5, which will focus on using SymPy to demonstrate the linearity of integration, both indefinite and definite integrals. Fairly straightforward, but it's a great reminder of linearity and constants, and also a good opportunity to continue practicing and further boosting your SymPy coding skills. Okay, so use SymPy to show the equality between these two expressions. So the integral of pi times x squared equals pi times the integral of x squared. Okay, so we know, or I claimed in this chapter, and I also demonstrated this in proofs, that constants in the integrands can be pulled out of the integral. Okay, so these two expressions look different, but they are really the same. And that's because the pi is just a constant. We can pull it out of the integral, okay? So what you want to do is write SymPy code that will print out this expression over here. So we have the integral of pi times x squared, and then pi times the integral of x squared. And these two results are equal to each other. They look a little different initially. I will talk about that when I show you the code. So this is for indefinite integrals, and then you want to repeat this using the same functions, the same constant, but for definite integrals. So you can set up the problem exactly the same way, but now you can integrate from 0 to 3 pi. And the key result here is that we get 9 pi fourths, so 9 times pi to the power of 4. In both cases, again, this is just a nice demonstration of the linearity of scalar multiplication inside an integral. Here I'm creating symbolic variables x and c. C is for the constant of integration. And, well, I already created these in the previous exercise, but here they are again. Okay. So here is a key part of solving this exercise. You want to define the function and the scalar as separate Python variables. And that's going to allow you to use them in different ways in different locations. Okay, so here I'm just printing out the function itself. Nothing fancy here. Okay, here's the key result, or the key code. Here I'm integrating s times f. So inside the integration function, we are multiplying by the scalar. And now here, inside the integration function, there is no scalar. There's only the function, the x squared. And then outside, so after we finish the integration, that is when I am multiplying by pi, by this scalar. Okay, and then, yeah, we see that they are the same. Now, these look initially different. You can see SymPy is multiplying through by pi to get pi c. But as I've discussed in this chapter and also in previous chapters, and I'll come back to this in subsequent chapters, unless we have some way to resolve C, like the initial value problem that you solved in the previous exercise, you don't actually know what C is. It's just some arbitrary constant. It's just some number. And so there's no distinction between C and pi times C or any other scalar times C or any number of C's. It can be C1 plus C2 plus C3 times pi to the power of E, whatever. They're all the same. It all just folds into one constant that we cannot resolve until we have some initial value problem. Okay, anyway, so that was for the first part of this exercise. Here we have exactly the same thing. The only thing I'm adding to this code here, these two lines, is the second input into sim.integrate. Instead of just being a variable, it's a tuple with 3 elements. So we have x because we are integrating with respect to x, and then we have the lower and the upper bounds of integration. And that's how SymPy knows to calculate a definite integral. And of course, those results are the same, not surprising. Now for exercise 6, in which we will demonstrate the additive property of integration. So there's 3 parts to this exercise. Similar to the previous exercise, we are going to demonstrate the additive property for indefinite integrals and definite integrals. And then we're also going to do some visualization to create one of the figures that I showed earlier in the book text. Okay, so to begin, implement these two expressions, these two functions, f of x and g of x, as symbolic expressions, so working with SymPy. So f of x is x squared, and g of x is 10 times the sine of x. Okay, and then we have another function, h of x, which is simply the sum of f and g. So pretty straightforward. So 2 unique functions, and then we create another function h simply by adding f and g together. And then the idea is to confirm that the integral of f plus the integral of g equals the integral of h, which is the integral of f plus g. So your SymPy code should create a figure or a text output, LaTeX output that looks like this figure. So here I'm printing out the integral of f, so the indefinite integral of f, here that is. Here is for g. Now these are done separately from each other. And here is f plus g. So this is the integral of f plus the integral of g. So that here you see the integral of f plus the integral of g equals this function, and here is the integral of h, which is the integral of the quantity f plus g. Okay, and then basically you see that these two terms are the same. Of course, we have some apparent differences with the constant of integration, but otherwise they're the same. Okay, so this is the first part of this exercise. The second part of this exercise is basically to reproduce this result. So still looking at the equality of integration for additive terms, but now we're doing this with a definite integral instead of an indefinite integral. So exactly the same procedure, but now we have bounds of integration. So we integrate from 0 to 3 pi. That gives us 9 pi cubed for f, 20, a value of 20 for function g, and then for function h, which is f plus g, we see, don't even need a calculator here, it's obvious that this integral here is just the sum of these two integrals. Okay, so that's the second part of this exercise. Finally, the third part is to write code to produce figure 8. Now let me scroll up to show you what figure 8 looks like. Here is the figure that we want to write code to create. You can even see we will create this figure in exercise 6. Okay, so here is function f of x, here is g of x, and here's the sum of those two functions. And you can see I've also drawn in the bounds of integration. So we want to calculate the area of this gray patch of the net total of the net sum of these gray patches, and here is the total area for h of x. Here you can see I'm defining these two functions, f of x and g of x, and of course h is just the sum of those two. And here I'm just printing this out for confirmation. Okay, here I integrate each of these functions so you can see f and g are being integrated completely independently of each other. And then here I'm calculating the integral of h, which is, of course, the sum of f and g. Okay, and then we print these out, and I just want to show you to highlight the code for this. So here what I'm doing is writing out the code separately for uh, fi plus gi. So this is the indefinite integral of f plus the indefinite integral of g. And here I'm printing out the indefinite integral of h. And you can see that those results are exactly the same. Again, as you know, you can ignore the constant of 2 for c. Okay, so then part 2 is really, really similar. There's not a whole lot you need to redo here. So we have the bounds of integration. Here I'm integrating again using almost exactly the same code, but now I specify the bounds of integration. And not surprisingly, those results are what I showed in the book text. Again, the point here is to see that for definite integrals and indefinite integrals, the integral of a sum of terms equals the sum of the integrals of those terms. And then finally, part 3 of this exercise is to write code to visualize that figure. Now, I'm not really going to go through all of the this code line by line, but just suffice it to say here I'm lambdifying the 3 functions, so f and g and f plus g. And just be mindful here, if you write in just the variable a here in linspace, you're going to get an error message. And that error message comes from the fact that linspace, and NumPy in general, is expecting a number, whereas a is defined as a symbolic variable. So you need to convert from the symbolic representation of pi to the numeric approximation to pi. So that's why I have all these floats floating around in here. Okay, yeah, I mean, you can look through all these lines individually. I'm not going to spend much time on them, just to show you that this generates the figure that I showed earlier in the book text. Welcome to exercise 7 of chapter 14. This is going to be a really interesting exercise because we are going to figure out a clever way to approximate an indefinite integral using definite integrals. Okay, so here's what we want to do. We are going to use the method trapezoid that implements the trapezoid rule, which you learned about in an earlier chapter with regards to Riemann sums. Okay, so SPI, the SciPy module for integration, dot trapezoid. Now, this function does not calculate an indefinite integral. It can only calculate definite integrals. But we are going to use that function to calculate or to approximate an indefinite integral. So how do we do that? Well, that is for you to find out. Or you keep watching and you see my solution. Okay, so yeah, you want to figure out how you can use a definite integral approximation to produce an indefinite integral approximation. You can start from this function here. Now, the interesting thing about this function is that it is analytically solvable. So implement this function in SymPy using symbolic expressions. And the reason why you should do that is because we can get an exact answer in SymPy, and that is going to allow us to compare our solution using the trapezoid method. Okay, so implement this in SymPy, and then you want to use SPI.trapezoid to calculate or to approximate an indefinite integral, and then you plot both. Okay, so here we see in this first figure, we are looking at the function that you see in the dashed line, and then here in the black line, this is the analytically solvable antiderivative from SymPy. Okay, so this is not yet an approximation. This is the exact antiderivative that we got from SymPy. Quite a long, complicated function here, but you know that's the result of SymPy. And then what you want to do is basically figure out how to reproduce this black line as an approximation using SPI.Trapezoid. Okay, and then let's see. Then you want to make this plot here. So here we see the dashed line is the same function that you saw in the previous figure. The black line here is the antiderivative from SymPy. So this is the like ground truth result. And then you can see the squares here correspond to the numerical approximation of the antiderivative using SPI.Trapezoid. Okay, and now there's just a little bit of a trick here, which is to figure out how to resolve the constant of integration. I will have more to say about that when I show you the code, but basically the output from SPI.Trapezoid is going to look like a shifted version of the analytically solved antiderivative. And so then, yeah, we need to basically come up with a solution to that. Okay, and then the final task for this exercise is to use the function SPI.Cumulative trapezoid and compare your results. So yeah, I'll talk about that in a moment. So here's for the first part of the exercise: create a symbolic variable x, implement the function, and integrate it symbolically. Okay, so again, we can use SymPy to solve this this integration problem and get an indefinite integral or an antiderivative. We do not need to approximate it for this particular function, but we will need to approximate it in the future. Okay, and here is, yeah, this first visualization. Now, in this case, I chose to use substitution and list comprehension to get these values. As I've discussed before, this returns a list. This does not return a NumPy array. But for reasons that you will see later, we actually do need this to be in the form of a NumPy array. So that's why I'm explicitly converting this list into floating point numbers and then into a NumPy array, both for the function and for the integral. Okay, yeah, so nothing super fancy here. This is the result that you saw before. Okay, now we get to the numerical approximation. Now, here is how you do this. Remember that an indefinite integral for each point x sub I of the indefinite integral is defined as the integral from minus infinity up to x sub I. Okay, so you can estimate numerically, you can approximate the indefinite integral by calculating the definite integral at each point of x, the definite integral from minus infinity up to that point in x. Now, we do not evaluate these functions out to minus infinity. So instead, we just evaluate them to, whatever is the first point that we happen to have, which is the value of x here. So we start from -2. So we're not evaluating the definite integral from minus infinity. We're evaluating the definite integral from -2 up until each point of x. And that is what allows us to numerically approximate an indefinite integral using a method that is designed for definite integrals. Okay, and this is in a for loop over all of the values of x that I chose to define up here. So -2 up to +5. Okay, this is for the next part of the exercise. I'll get back to that in a moment. Okay, so now for starters, let me just delete this for a moment. Okay, so here you see I'm plotting the function, npi is for numpy, of course. I'm plotting its integral, so it's indefinite integral. And this comes from SymPy, okay? So this is the exact result. This is the analytically derived solution. And now here I'm plotting the SciPy approximation that we just calculated up here in this for loop. Now, when you look at these initially, they appear not to, okay, let me just take off the legend just to make this a little more visible. It looks like these do not overlap, okay? So here the black line is the true result and the squares are the approximation. It looks like our approximation is wrong. But you see the waveform shape is really similar. They both go up and then down a little bit and then up again. So in other words, they appear to be matching except for a constant, a shift on the y-axis. And this is the constant of integration that is separating them. Now, in this case, we do not have an initial value constraint. Okay, so there's a number of ways that you could resolve this to get these to match. What I did here is really just rely on some visualization. So I'm just subtracting 6.1. That's just based on some trial and error, visual inspection, and then just coming up with a constant that seems to make them match. So the waveforms match, so the shape of the integral and its approximation match. And we do not have a initial value problem, so it's not really possible for us to resolve the initial value problem. Now, there are some solutions to this. I'll talk more about this in later chapters, in particular a chapter on multivariable integration. But one thing you can do is just have these functions set to be, have the antiderivative set to equal 0 at x equals 0. So I could have shifted this so that it's 0 at 0. So the antiderivative would cross the origin. That is a correct solution. It is not necessarily the only correct solution because we do not know what the correct solution is. We have this indeterminacy of the constant of integration. So in this case, I chose a constant of integration to make the plot look nice, to show us that the numerical approximation is a good match to the exact value that we can calculate in SymPy. Okay, so the final part of this exercise is to use the cumulative trap function in the SPI module. So then what we're going to see is that basically this result here, this result, is identical to this result. So our approximate integration by using definite integrals is basically also what SPI.cumulative trapezoid implements. Okay, I'm going to ignore that for a moment. And then just get back to this plotting here just to show you that now, again, we have exactly the same result. In practice, of course, it's better to use a function like this instead of having to deal with multiple lines of code and for loops and so on. But what I like about this manual implementation here is it really highlights the link between the definite integral and the indefinite integral. Exercise 8 is a follow-up to exercise 7. So in the previous exercise, we approximated the indefinite integral of a function using definite integrals and then also using the function cumulative trapezoid. Now, in that example, in the previous exercise, that function was also analytically integrable. So we could use SymPy to calculate the exact integral. But in this exercise, we're going to use a different function that SymPy cannot integrate. So here's the function. F of x equals the ratio of e to the minus x squared in the numerator and e to the x plus 1 in the denominator. Now, I would like you to try integrating this function in SymPy and, well, see what happens. You might be a little bit surprised or possibly unhappy with the results. And then what you want to do is basically use substitution to get numerical results, and then use cumulative trapezoid, this function in the SciPy integration module, to approximate the indefinite integral. Okay, so you can recognize a lot of this from the previous exercise. You can reuse a lot of code from the previous exercise. Then you want to generate this plot. So here I have the function as a black line and the numerical approximation of the indefinite integral or the antiderivative in the dashed gray line. Okay, and then one of the parameters that you need to specify in the cumulative trapezoid function is delta x. And so typically you would specify delta x as being, the difference between two successive x values. Okay, so x1 minus x0, where x or xx is the vector of x-axis grid values for evaluating the function. Okay, and then the last part of this exercise is to figure out what would happen if you input xx2 minus 0 instead of xx1. So this is the correct syntax. This really is dx, delta x. Here, this is actually 2 times delta x. So this, if you wrote this in the function, that would be a mistake. That would be a coding bug. And the question is, what does that do? What is the impact of that coding bug? I would like you first to make a prediction, just to think about what would happen, and then implement it in code to test your prediction. And then the very, very last part of this exercise is to change this back so that your code is correct instead of having this bug intentionally left in there for the future. Okay, so here we see the implementation of the function and also my attempt to integrate it using sim.integrate. And then here I'm just printing out these two results. So the function itself is fine, although interestingly, Python or SymPy does rearrange the function to make it look a little bit different, right? So here I very clearly write that this should be a fraction. I'm using a division sign. But instead of writing e to the x plus 1, so plus x plus 1, instead, SymPy is getting rid of the fraction altogether and writing e to the minus x plus 1 or e to the minus x minus 1. Exactly the same. It just looks different from how we implemented it here. Totally fine. Okay, so here's the integral, and we don't really get anything. So again, we get one of these situations where the output is the same as the input. Okay, so the integral of this function is just the integral of the function. Python is not able to, or I should say SymPy, is not able to evaluate this analytically and give us a solution for the antiderivative. All it did was recognize that it can pull out a constant e, and then it just divides that constant. So that is for the indefinite integral. What happens if we try to get a definite integral? So here I'm just adding bounds. This is, just to see if we can get a numerical result. And here again, we don't. We just get the same thing just with bounds. And, if you try to run eval f, you're still not going to get a numerical result here. You're still just going to get the actual integral itself back. Okay, so now, let's see what happens if we try to substitute specific values. So here I'm using substitution and list comprehension to try to get out a bunch of values. This is from the previous exercise, but it doesn't really matter. Just trying to get out numerical values from this integration. And here, yeah, we haven't made any progress here. This is just telling us the integral in text, exactly what it shows up here in LaTeX code. Man, there's really a lot of this. Let me just get rid of this. All right, so still having lots of problems. Where are we? Here we are. So therefore, what I'm going to do is use list comprehension and substitution to get the values of the function. These are not the values of the integral of the function. They are the values of the function itself. And then I'm using cumulative trapezoid to actually get a numerical approximation of the integral, the indefinite integral. Okay, and then I'm visualizing them like this, as you saw in the figure in the book. Okay, so then the last piece of this exercise was to imagine what would happen if you have a typo like this. Now, where did I get the idea to make this part of the exercise? I will tell you, this was a literal typo that I made, and I eventually caught it, but I thought it was an interesting typo to include as part of this exercise to give you the opportunity to explore this. So essentially the impact here is that we are defining delta x to be 2 times what it really is. So this is the true delta x like this. And now basically I'm just saying that we have 2 delta x. So delta x is twice what it really is. Okay, so let us observe the waveform shape. It looks a bit like a sigmoid function or an S-shaped function. And then we can look at the numerical values. So it starts at 0 and it goes up to, looks like it's asymptoting at around 0.8. Okay, so now I'm going to run this again. And we can see the waveform shape is the same. It still looks like a sigmoid. The shape looks the same, and now it's asymptoting at what is plausibly 1.6. So the scaling factor is off by a factor of 2. And that's not surprising that it's off by a factor of 2. You can try this again with setting it to be 3 and see what happens there. This is just a little suggestion. You can print out the final value of the approximation of the indefinite integral just as a way to help you understand the impact of this mistake in there. I'm going to set it back here so it doesn't forever stay as 2 minus 0. Exercise 9 is a really interesting exercise. I think you're going to enjoy working through this one. You're going to work on lots of skills in SymPy with integration, and in particular, we are going to focus on the challenges of constants of integration in a function that has a discontinuity. Okay, so we are going to be working with this function here. It is f of x equals e to the power of p divided by q, where p and q are these polynomials. So implement this function here, actually implement these 3 functions, because we're going to be working with p divided by q separately and visualizing this. Okay, then you want to approximate its antiderivative using cumulative Simpson method that you already know how to calculate. This is the same as cumulative trapezoid. It's just a different method, as you know from earlier in the text. The trapezoid method involves trapezoids, and the Simpson's method involves estimating polynomials, but it's really, really similar. Certainly, running this function in the SciPy module, so the code is basically the same. Okay. Then what you want to do is visualize the rational function inside the exponential, so p divided by q, as its own function in its own plot. And then you have the function itself here in the black line. Now what you see is that there is a discontinuity here at somewhere around 0.3. So yeah, it's around 0.386. We're also going to calculate the exact value in SymPy in when I switch to the code. But anyway, somewhere around a third, there is a discontinuity here. So this side here to the left goes down to minus infinity, and this side here on the right comes down from plus infinity. Now, when you go towards minus infinity in the exponent here in this function, when you have e to the this rational expression, that simply goes to 0. This does not go to minus infinity because this black line is e to the power of something, and e to the power of anything cannot be a negative number, right? E to the p divided by q is a strictly positive function. Okay, so here we go down to 0. That's okay. But over here, we do get a discontinuity coming down from plus infinity. So that kind of matches this. Okay, so now the question is, how do we deal with a constant of integration in the numerical approximation of the indefinite integral here? And that's what you see with this gray line. Now, there's a couple of ways you can do this. I would like you to take some time to explore different options and why this even is an issue, why this is necessary to address this situation. Basically, what I did is exclude the function numerical values very close to this discontinuity, and then I took this function and shifted the antiderivative up so that it matches with the final value before we get to this discontinuity over here. Okay, here we are in the code, and we're just going to play around and explore this function and its integral a little bit. Okay, so here I define the two functions, p and q, and then here is the main function that we are going to be working with, which is e to the p divided by q. Okay, and then, yeah, let's see. Here well, you've seen this code before. This is just a little bit of a hack just to remove that vertical line. In fact, I'll even remove this just to remind you what this looks like. Okay, so let's see. For now, in the plot, here you see p divided by q. Again, this vertical line here, this is something I've discussed earlier in the book in a previous chapter, this vertical line is specious. It is incorrect. There are no function values that actually correspond to this line. This is just an issue with visualization in Matplotlib. Same thing here. This vertical line here, the black vertical line, does not really exist. This function comes down from minus infinity up here. There is no function values on this line. Okay, so that is why I basically just find the infinity point and set those to be nan in the function and in p of x. And basically that just gets rid of that visual appearance of that line there. Okay, so now you can see there's no indefinite integral after this discontinuity. So where did it go? Maybe you think it's being plotted all the way up here. You can try extending the y-axis boundary. It's not there, okay? And to show you that it's not there, I'm going to just look at the numerical value. So this variable is called f int. So f int, and here we see we get some numbers and then we get nans. So what's happening here is that the value here in the function is coming down from minus infinity. I've set it to be nan. The function cumulative Simpson is just calculating the sum, the cumulative sum following the Simpson rule. Okay, so what I am doing here instead is calculating the indefinite integral twice. So once before the this discontinuity here that gives us this line, and then I'm calculating it again after this discontinuity. Okay, and that is what you see in this line here. So the f inf point, so this is the point where we have an infinity value, and now I'm adding a little bit. This just accounts for these really large values here. So I just want to ignore some of those when defining the constant of integration. And that's what I do here. So you can see I'm calling this function spi.cumulative-Simpson twice. Essentially, this means that I am calculating the indefinite integral as a two-piece, piecewise function. One piece is before the breakpoint and one piece is after the breakpoint. All right, and then you can see that result here. So now the second piece actually continues down here. Now, there's nothing wrong with this. This is fine, but I think it looks a little bit awkward. So what I am going to do now is shift these values, shift the second part of this indefinite integral. So modify the constant of integration just to visually make these two pieces be more consistent with each other. And that's what I do here. So here I am shifting this part of the indefinite integral that I'm calculating here. I just shift it up to be equal to, or to have a shift of, the original part, so the first part, and then a little bit before we get this break. Okay, and that looks like this. Very good. And then there's one more piece that I want to do, which is to shift this indefinite integral so that the indefinite integral and the definite integral meet at -3, so at the beginning of x. Again, these are kind of arbitrary choices that I am making in order to get the plot to look nice. And why do I want the plot to look nice? Well, it just helps with the visual interpretation. But the point is that everything that I'm doing here are all correct solutions to this problem. The issue is that we are dealing with a constant of integration, and the constant of integration cannot be resolved without any numerical constraints. And because these are made-up problems, we don't necessarily have any constraints that come to us from experimental data or from observations about the natural world or from physics or from engineering or biology. So we can kind of play around with these constants of integration because they are indeterminate. Okay, the last thing I want to show is finding the exact numerical value corresponding to this discontinuity over here. So here I am using sim.solve for finding the roots of this expression. Now, this is a third order polynomial, so it's going to have 3 roots. This comes from the fundamental theorem of algebra, that we know that something of, x cubed, or in this case, I'm using b just to avoid overwriting x, but a variable cubed is going to have three roots, three solutions. But that doesn't mean that they are going to be real valued. And that's what you see here. So sim.solve gives this crazy looking long output. You can see it's organized as a list. And if we look for commas to separate the elements of this list, we can find 2 commas here and here, which means that there are 3 solutions, as I said. But when you look at this first solution, you can see it has an I, right? So this is the square root of -1. This is a complex result. This is also a complex result. So the real valued result is in the 3rd position, and that you can see here. And this is just a really long, complicated looking thing. But these are all numbers, right? This is just a numeric result. There's no variables in here. So now I'm using eval_f to give us a numerical approximation of that exact result, which included square root signs and so on. And basically this tells us that when x equals 0.386, etc., then we have this discontinuity over here. Welcome to exercise 10. This is going to be a really interesting exercise focused on the x-axis grid spacing and regularity of that spacing, and how that impacts the definite integral, or the approximation of the definite integral of a function. Now, so far in this entire book, we have been estimating functions using a regularly spaced x-axis grid. That is to say, the distance between each successive x-axis value was exactly the same everywhere in this book. So delta x was always the same for every value of x. But that does not necessarily need to be the case. We can define functions using x-axis values that are irregularly spaced, so have different spacing, different gaps or distances between successive x-axis value points. So that's a pretty interesting thing, and we are going to explore in this exercise the impact of irregular versus regular sampling. All right, so here is the function we are going to work with. F of x equals x squared plus the cosine of x plus x. So implement this as a SymPy expression and then lambdify it. And that is basically going to allow us to evaluate numerically this function for lots of different arbitrary values of x. Okay, so then you want to create 2 sets of x-axis grid points. One is regularly spaced numbers between -2 and +4. That's exactly like how we always do in this book. But then you create a second set of x-axis grid points where you have 555 randomly sampled points between the same 2 bounds. So between -2 and +4, you create a random subset of points. So random numbers generated between -2 and +4. Now, in these 2 sets of x-axis grid points, they have the same number of points. They have the same bounds, the same lower and upper bounds of those points. The difference is that in one set, the delta x is constant, and in the other set, the delta x is random. It varies as a function of x. And that's what you see in this figure that you are going to create as the first part of this exercise. So here we have, for regular x and random x, this is the x-axis value. Now for regular x, with increasing sample index, the x-axis value simply increases linearly, and that you see with so it's a straight line, no surprise there. And then the random x is increasing monotonically because I've sorted them, so x is always increasing. But sometimes it increases by a lot, and sometimes it increases by only a little bit. Again, that is because we are randomly sampling. We are generating random x-axis values. Okay, and then here you see the delta x. Now for the regular x-axis grid spacing, delta x is a constant. It's whatever the numerical value is. It's a little bit over 0.01. It's the same exact value everywhere. But for random x, of course, delta x is varying randomly. That's how I defined it. Okay, now what you see here is the plot of random x and regular x, and visually they look the same. So when you look at this plot, panel C here, you would come to the conclusion that the random versus regular spacing does not matter. The function looks the same. Now, on the one hand, from visual inspection at this level of resolution, that is a perfectly valid conclusion. And the rest of the exercise is focused on evaluating whether that conclusion really holds and whether we can generalize that conclusion to calculating the definite integral. Okay, so here is what you want to do. Calculate the definite integral of this function between -2 and +4 four times. So 4 definite integrals. First, we calculate it in SymPy. And the reason why we're doing it in SymPy is to get an exact result. So this gives us a ground truth method that we trust. And then we want to know whether these other 3 results, which are approximations, are going to be consistent with the SymPy result that we take as the exact solution. Okay, so we have from the regular x, we have 2 different approximations. One where we specify x equals in spi.simpsons. So the second input into spi.simpson is the x values. And then we also specify the dx values. That's the second one. That's this one here. And then we specify, or we use spi.simpson, but using the irregularly sampled x-axis grid. Okay, I am going to now switch to code and show you my solution, and then I will have a brief discussion about these results. Here you see the 2 sets of x-axis values. So these are the bounds, A and B. Here I'm specifying that we have 555 elements, and for the regular x-axis spacing, this is just n linearly spaced numbers between A and B. Nothing surprising there. Here is where I use the numpy.random.uniform function. So I'm going to be randomly generating numbers from a uniform distribution. So every value between A and B is equally likely to be selected. And we have 555 of these as well. Now, these are not in order, but I want to plot them in order. So therefore, I'm using the sort method on this NumPy array to give me sorted values. Okay, now here I'm calculating the dx for the regular sampling, and that is just the first value or the second value minus the first value. Okay, here I'm defining the function x squared plus cos x plus x, lambdafying it, and then I get 2 sets of function values. So the same function, right? F lam, same function that we're using here, but we are either querying this function, evaluating this function, using the regularly sampled x-axis grids or the randomly sampled x-axis grid. Okay, and then, yeah, I'm plotting those. And here to get the second plot, I'm using the numpy.diff function. So I'm basically differentiating this random function to get the delta x values. And that's what you see here. Okay, so this just reproduces the plot that I showed in the text. Now, the gray line should always reproduce exactly the same result. The black dots come from randomly sampling. So those numerical values, how exactly this plot looks, is going to be different each time you rerun the code. We can actually do this here. So notice there's 2 dots clustered together here, and then we have 1, 2, 3. Okay, and now I run it again. And the overall, general characteristics look the same. But of course, the exact values are changing each time I rerun the code because I'm generating new random numbers. Here is the code for the 4 different integrations. So I say all 3, but it's all 3 approximations. So I'm using sim.integrate. So this gives me the exact result. Here I'm using, in these 3, the approximations are always using the same method. So it's always using spi.simpson. Using the random or the regular, and the regular I'm using twice, by defining x and by defining dx. Okay, and then we can see the results. Now, these three results here match exactly what I showed in the book because these are based on deterministic calculations. In contrast, the x rand is going to look different each time I rerun it. Now, in this case, the numerical approximation happened to be a little bit closer to the exact result compared to what I showed in the book text, but that's just random. You saw yourself. We just randomly generate these values each time I rerun this code. So now I'm running it again, and you can see again, these three results match because spi.simpson is a very accurate approximation. But when we irregularly sample, we risk getting a reduced approximation accuracy. So I hope you found this exercise interesting. You might be wondering, what is the point of randomly coming up with numbers? Isn't it always better to have regular spacing? The answer is yes. It is oftentimes better to have regular spaced numbers for evaluating mathematical functions, but we don't always have that luxury, especially if you are working with applications and with experimental data. You might have constraints due to the features of the experiment you're running or the data set that you're getting. There might be missing data values. There might have been problems with the equipment or the calibration of the sensors. So this is a very realistic kind of scenario.